So I was going to make a video saying section 4.4 in the textbook is not actually part of the course, but it's interesting and it is very much like what we did back in chapter 2 when we were doing, chapter 3, I guess, when we were doing second order equations, but it's variations of parameters just with higher order differential equations. And I was going to leave it at that. But then I thought, meh, let's just do one example and so you can see how it's the same. But, this isn't going to be a short video. So here we go. I'm just going to do the example of y triple prime minus y prime equals t. So first, to solve a non-homogeneous equation, you got to solve the homogeneous one. So put a 0 over here. And then what do we have? The y triple prime turns into an r cubed. Right, we're assuming y equals e to the rt is a solution, and then we got to find the r. So the r will work if you can get r cubed minus r to equal 0. Factor an r out, the r squared minus 1 is r plus 1, r minus 1. And so I've got r equals 0, r equals minus 1, and r equals 1 as my solutions, which give me 3 independent solutions. Y equals 1, that's from there. That's e to the 0t, and then e to the minus 1t, and e to the 1t. Right? And because I know what I'm going to do later, I'm just going to get the Wronskian of those 3 things right now. So there's the 3 functions. And then take their derivatives and the derivatives again, and then take the determinant of that, and the determinant here is -2. All right. Bell's theorem would have probably told me that as well. Anyway, so now, how does this work? So we are now going to look for a particular solution to this differential equation right here, right? And we're going to do variation of parameters. Now, we do this by saying that we're going to look for y sub p by finding u1, u2, and u3, so that when we multiply them by y1, y2, and y3 and add those together, the result is a solution to the non-homogeneous differential equation. So if I'm going to plug this into the differential equation, I need to take a bunch of derivatives, right? In this case, it's a third order differential equation, so I got to get all the way up to the third derivative. So the first derivative looks like this. There's 3 product rules. And then rearranging, it looks like this. So I'm putting all the u's first and the u primes second. But then it's like, I really want those u primes to be, those 3 terms to add up to 0. So I'm going to assume that they add up to 0. Now this is just putting a new condition on the u's. I mean, there's a lot of flexibility here in what u can be. So throwing one condition on just limits what they might be, but still I think leaves enough room to maybe find an answer. But the result is that it looks like when you took the derivative that the u's just acted as constants, right? They didn't really, there was product rules, but because you made those zeros, these just look like constants. So the derivative of u1, y1 was u1, y1 prime. The derivative of u2, y2 was u2, y2 prime, and so on. Then you take the next derivative, and again, you've got 3 product rules you got to do, and I rearrange them so that the u1, u2, and u3 are out here at first, and the u1, u2, and u3 primes are all over there. And then it's like, hey, you know what? I want these to equal 0, add up to 0 as well. So let's assume that those last 3 terms add up to 0 as well. And then now it looks like, again, the u1, u2, and u3 acted as constants when we took the derivative. And lastly, there's the third derivative right there. And well, now what I'm going to do is I'm going to take all that stuff and plug it into the original differential equation. And the original differential equation was y triple prime, all right, I've forgotten already, what is it? Y triple prime minus y equals, y triple prime minus y prime equals t. Okay, so here's, where am I? Yes, here's y triple prime, and then minus y prime, and that's supposed to equal t. Now I'm going to rearrange some things. So I notice there's this term right here, and another one. this one right here that have a U1 in it. So I'm going to put them next to each other and factor out the U1. Likewise, I see a U2 here and a U2 there. I want to run, I want to hide. And then there's a U3 here and a U3 there. And so again, get those together. Notice though, in the parentheses, what you have is y1 triple prime minus y1 prime, which is precisely y1 plugged into the left-hand side of that equation. But y1 is a solution to the homogeneous equation. So when you plug a y1 in here, you get a 0. Likewise with y2 and y3. So the stuff in parentheses there, dun, 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 are all 0, 0, 0, 0. And so those go away and you just get u1 prime y1 double prime plus u2 prime y2 double prime plus u3 prime y3 double prime equals t. And so what I ended up with here now is I have three conditions that need to be true because I assumed that this was 0 and I assumed that that was 0, and then I now have that this has to equal t. And it turns out that well, it equals t in the event that this was a general linear differential equation. That would have been a g of t over there on the right, and there might have been more stuff to plug in, but the stuff in parentheses would have all turned into zeros again, and you'd have a g of t right here. So for this example, it's a t, because that's what g of t was. But I rewrote it here with a g of t there, so sort of give the general sense of what's happening here. That I now have a system of three equations and three unknowns, where the unknowns are u1 prime, u2 prime, and u3 prime. This is very much the same as what happened with second order, but we just had the u1 prime and u2 prime. Now we've got three of them, right? And you could imagine in a fourth order differential equation, you'd have a 4x4 determinant here, or not determinant, but a 4x4 matrix, and four variables, u1 prime, u2 prime, u3 prime, and u4 prime. Right? Anyway, use Cramer's rule to solve this. So u1 equals, this is the determinant of the coefficient matrix, and the numerator is the determinant of, since I'm solving for the first variable, I replace the first column by the stuff that's over on the right here. And then when I solve for the second variable, I replace the second column by what's on the right, and likewise for the third one. Notice that the denominator is actually the Wronskian of those three functions. And also notice that I'm solving for u1, u2, and u3 prime. So in order to get u1, u2, and u3, you've got to integrate. So I have the integral of this determinant divided by the Wronskian for u1, and then for u2, it's the integral of this determinant divided by the Wronskian, and so on. And you can see that this would generalize very nicely to any nth order differential equation. So here we go. Not any nth order differential equation, but nth order linear differential equation. So in this case, I have that the Wronskian was -2, and I replaced the first column with 0, 0, t, and there's the rest of it. So when I take that determinant, this is going to be plus minus plus, so it's plus t times this subdeterminant up there, and that's a 1, and that's another 1. Actually, that's -1, but you're subtracting, so 1 minus -1 is 2. So the numerator just is 2 times t, and the denominator is -2, so that integrates to -t squared over 2. Likewise, u2, here's this one with the 0, 0, t in the second column. Taking the determinant of that 3x3 matrix there, you get -t e to the t. And so integrating, there's an integration by parts that has to be done. Anyway, it turns out to look like that. And notice I'm not worrying about the plus c in either case, because I don't need all of the u1 and u2s that work. I just need one. Just need one. So I'm using c equals 0 here, plus 0 each time. And likewise here with the u3, the 0, 0, t is over here in the third column. Take that determinant, and again, you're going to have an integration by parts and end up with this. So then yp was u1 times y1 plus u2 times y2 plus u3 times y3, and in each of these two, the e to the t times e to the minus t is just 1. And so then you have so that looks like that, right down there. And then there's a plus a half t and a minus a half t that goes away, and there's a minus a half and a minus another half, which is minus 1. And so y sub p looks like this. And just to double check that this is supposed to be a solution to that original differential equation. So just to double check, let's do it. Let's take that's the function, take the derivative, take the second derivative, take the third derivative, and plug it in. Remember, the differential equation was y triple prime minus y equals t, but here y triple prime of 0 minus y prime of negative t is t, and it works. Okay. Now, this is a little odd in that because this is a t over here, I could have used the other method of undetermined coefficients, but I just wanted to illustrate variation of parameters. Okay, this is not actually part of the course, but I think it's worth seeing that the process that we learned for second order is very much expandable for higher order linear differential equations.